Hi everyone, in this video I'm gonna show how to solve this problem in measure theory. So if we have a measure space and we have a sequence of non-negative measurable functions converges to f pointwise, then if the limit of those integrals equals to 0, we'll have f itself equal to 0 almost everywhere with respect to the measure. So first, before going to prove the result, I think it's important for us to have another result in mind, which is if we can show the integral of f equal to 0, it would give us f itself must be identical, must be 0 almost everywhere. So why is it? It's because what we're going to show is essentially the measure of the set which f is not 0, or maybe we can start with the measure of the set which f is strictly positive is equal to 0. So in order to deal with those sets, we can just utilize the union of I1 over I, which is a commonly used trick to deal with those kind of thing. So the union of those sets where J is integers or natural numbers, and is actually all the where f is strictly positive. So in that case, suppose f is not identically 0 almost everywhere. We can find one of the set to be to have the strictly positive measure. Then the integral of the entire f is gonna be greater than the integral of f over some set which f is strictly bigger than 1 over j. And as we can change that into the measure of the, it's by using the indicators. So which is f times indicator of and then it's clear that this one would be greater than or equals the measure of this times over j, right? Because we have f itself is strictly bigger than j, bigger than 1 over j. So let me write it. So this integral would be greater than the 1 over j times f times the indicator function of f. And 1 over j is a constant, so this part is just the measure of the set. So we have the inequality here. And this one is strictly bigger than 0, so we get a contradiction. Thus, by contradiction, f must be 0 almost everywhere. So if we have this fact, then it's easy to use this fact to show f is actually equal to 0 almost everywhere, because we can use Fattou's lemma to put the limit inside of the integral and get the result. So let's recall Fattou's lemma. So Fattou's lemma is if we have a sequence of function fj, and it's a sequence of non-negative functions, and the lim inf of the sequence would be smaller or equal to the lim inf of the integral of the functions. Okay, now another commonly used trick is if we have the limit exist here, then by the simple result from real analysis, we know the limit itself has to equal the lim sup and lim inf. So we can use that to interchange the limit and lim inf. And also in this part, as the limit also exists, so we can do another change. This one would be equal to just the limit itself. Which is 0. And then recall that we're dealing with non-negative functions. So the integral of non-negative functions must be greater or equal to 0. Then we can kind of squeeze this, show that the integral itself must be 0. And by the result we proved before, f itself must be 0 almost everywhere.